So finally today I'll get back to my objective in the first lecture, that is to study mean normal regression for the neural tangent model of a two-layer neural network. So the model is this one. So this is the featurization map, and you have a linear model with this featurization map, and so you can think of doing either so this is number of parameters n times d, and you can think of either fitting the b parameters or equivalently, of course, you can think of doing kernel regression with the kernel that is the kernel matrix that is given by this featurization map. Okay, and we saw at least formally that as capital N goes to infinity, this kernel converges to pointwise to some inner product kernel. And in the last lecture, we studied the risk of this inner product kernel. And now my objective is to understand, okay, what does it mean and going to infinity? What does it mean with going to infinity? Does the width have to be exponentially large in the dimension or in the sample size, or perhaps much less is required? Okay? So I state the results in terms of comparison between three risks. Well, the first one is the risk of the neural tangent model at a target function f star. So as before, my model will be that here the xi are uniform on the sphere of radius square root of d, and the yi are equal to f star of xi plus some epsilon I, where f star is just a function in L2. And the epsilon I have variance tau square. And as I was saying, I will compare three risks. The first one will be the risk of the neural tangent model at a target function x star with regularization lambda. Just let's rewrite it once more, just to be sure that we all agree what this is f star of at a new test point minus really b lambda phi x nu. So this is, then there will be the risk of KRR f star lambda. So this is kernel ridge regression with this infinite width kernel. And then there will be another object that I will compare to. We saw in the last lecture that kernel ridge regression can be approximated. The risk is similar to the risk of polynomial ridge regression. So let me call it L f star lambda. And this is basically the risk of doing linear regression, ridge regression with respect to the polynomials of degree L. Okay, so this is basically a finite dimensional regression that has roughly d to the L parameters that I'm fitting. Okay, so correspond to, equivalently, polynomial ridge regression is equivalent to doing kernel ridge regression with respect to the kernel that is K. Okay, perhaps I should remind you that the kernel K can be expanded in the basis of spherical harmonics. So this is a polynomial of degree m is of degree m in each of x1 and x2. So polynomial ridge regression is ridge regression with respect to kernel ridge regression with respect to the kernel that you obtain by truncating this one at level L. Okay, is everybody fine with this setting? Okay, so we want to compare this to this that is formally the n infinity limit, and of course to this because we saw that the two of them are related in the last lecture. And okay, the results that I state are under a couple of assumptions. So assumption 1 is about the sample size. So I'll assume that, okay, d to the L log d. So it's a similar separation assumption as I described in the last lecture for kernel ridge regression. So n basically is polynomial in d, but is not an integer power of d. This is for some big power, for some big constant c. Okay, so this is for some L. Bigger or equal than 2, and for L equal 1, actually there is a weaker condition that we can deal with, is n over c bigger or equal than n bigger or equal than d square log d square. Let's call this C0. So for this first case, the case in which n is between d and d square, we can also afford n proportional to d in this result. And then, okay, there is an assumption too about. I'll put it in the statement. There is another assumption about the activation function that I'll put in the statement of the theorem. Okay, so, erase this. So notice, by the way, now I erased it, but by the way, that this featurization map corresponds really on the case in which you linearize the two-layer network with respect to the first layer, okay? I could have added also the term that comes from the second layer. This corresponds basically to add a piece to the kernel. Okay, let me write it. Explicitly, the kernel that I'm working in, the finite width kernel, is what? Is 1 over nd, sum over I 1 to n, and then there is x1, x2, sigma prime wi transpose x1, sigma prime wi transpose x2. You know, if you also add the term corresponding to the second layer, there is another term here that is I1 to n, and then sigma wi transpose x, sigma wi transpose x, 1, x2. Okay? So this is what, okay, in our papers we call really this the neural tangent kernel, and this is the random feature kernel, because it's really the kernel that corresponds to passing a neural network to data through a random neural network and just fitting the second layer. In practice, you know, this doesn't give you much on top of this, because this is much lower rank than this. This is only rank capital N, while this is typically of rank, you know, capital N times capital D. This corresponds to fitting D parameters, N parameters, and this is correspond to fit N times D parameters. So the really important part in the two-layer network is that one, right? Okay, so if you now look at multi-layer networks, of course, you know, there will be a sequence of kernels, and now you cannot neglect any of them if you go beyond two layers. Okay, now I'll erase this. So the theorem is joint with Yichao Zhang. And okay, we have very weak assumption on sigma, so we only need sigma weakly differentiable So for instance, ReLU is okay, means almost everywhere differentiable with the continuous derivative will be fine. With the continuous function will be fine, and then we need that sigma prime of x is less than a constant times 1 plus x to the b. Okay, so pretty much everything that you can think of is fine. And then the other thing is that we need the following constant. So v sigma. Okay, perhaps I should call it consistently with other lecture, lambda star of sigma. So this would be the sum over k bigger or equal than L of. So what is this? Take sigma prime and project it onto Hermite polynomials and take all the coefficient after L of sigma prime, and you project it in the Gaussian case. Okay. Equivalently, this is the minimum over all polynomial p of degree L minus 1 of the expectation of sigma prime of g minus p of g square. Okay. So it must have some, the sigma prime must not, shouldn't be a polynomial of degree L minus 1, basically. So we ask this to be strictly positive.
Is this a different lambda star from the lambda star 2 lectures ago?
Yeah, but it plays the same role, and this is okay. If you want, I had it in my note. I called it, and in the paper we call V. But now it occurred to me that philosophically it's the same object as the lambda star that we had. All right, it's very similar. So okay, let me call it V, just not to make confusion. Okay, and then final assumption, we need that the network is a bit overparameterized. Okay. Okay, then we have the following. If you look at the risk of NT, F star at regularization lambda, this is the risk of KRR F star lambda plus something that is of order, okay, let me call it tau plus square so there exists a constant C that depends on all the constants that I gave before, such that you have this error thing, and here tau plus square is just the noise plus the second moment of the target function. Okay, so this is what is, so let's pause a minute. This is what it's saying is that, if when is this small, forget logarithms, is small when capital ND, so the number of parameters in the network, is bigger than the sample size. It's much bigger than the sample size. So as soon as this is much bigger than the sample size, this is small of 1, and what we get is that the anti-risk, the neural tangent, behave as the infinite width kernel. Okay?
Is the C dot in the condition the same as the C in the...
No, this is, okay, I should call it, I should have written, all the quantifiers here are, we assume, there exists a constant C large enough such that if this holds, then there exists another constant C prime such that this holds. Okay. Now, of course, I don't expect this log ND is spurious. It's just because we only wrote whatever 30 pages proof. Somebody much smarter than us should be able to remove this log ND, right? But okay. So does this statement make sense? But apart from this logarithmic term, this is really the behavior that I expect, correct when you over-parameterized. As soon as you are over-parameterized, then the two are approached. And this is also equal. Okay, this is a version very similar. Oh, this is similar to what I had in the last lecture, except with an explicit error term. So we saw in the last lecture that this is approximated by polynomial ridge regression lambda plus V sigma. So you saw that kernel ridge regression is equal to polynomial ridge regression in which you increase lambda by an extra term that is self-induced regularization plus basically the same error. Okay, there is two terms of error. Okay, perhaps let me write it there because here it's not easy to see. This is equal to risk of polynomial ridge regression at level L, F star lambda plus V sigma plus order of square root of n over nd log nd to the C, and then plus order of there is this tau plus square times okay, so this is what we saw, or similar to what we saw in the last lecture. This is approximated by polynomial ridge regression. If I shift the regularization, this is the same error that I had here. So this is the finite width error. Okay? And instead this term is the error you see. This doesn't depend of this is the error that is approximating polynomial ridge regression by kernel ridge regression. And you see that is small when small n is much smaller than d to the L plus 1. I wanted to say something. Okay. Any question about this? Yeah.
Do you have a vivid picture about why the difference between finite width and infinite width depends also on the norm of the target?
Well, everything depends on the norm of the target here. Remember, okay, so good question. Here, what is the place, the role played by the normal target? Remember that what we are looking at is, okay, the risk of any of this thing is okay, and as we explained this, we can decompose into a bias and a variance. So this is expectation with respect to x, and remember is also expectation. Okay, this is what I wanted to say. These are all the way I define them. I define them as a first, in the first lecture, the expectation is with respect to epsilon 1, epsilon n, and the last and the test point. So I'm not taking expectation over the data. So these are all random quantities. So this means that these all the equalities hold with high probability, or this inequality hold with high probability. So you can say this by saying this holds with high probability. Actually, I think in the paper we have explicit probability bound, or you can do as probabilists do, that is just write a p here, which I like more, but then if you submit at certain conferences, they don't understand it. Okay, so you can do this, and then you can decompose this in the bias and the variance. Okay, and if you think about it, the variance, the bias is linear in F star. So this is linear in F star. I mean, this argument here is linear in F star. So this whole term is proportional to the norm of F star squared, the L2 norm of F star. This whole term doesn't depend on F star. The variance is independent of star, and instead is proportional to tau square. Okay? So really the risk is that the sum of two terms is the sum of a term that is F star square L2 times bias, or bias normalized, and plus tau square times variance normalized. Yeah, so exactly. Yeah. And so the way you really prove it, the theorem is that you look at these two pieces and you approximate these, and then you get an extra multiplicative factor, right? Like that. Any other question about this statement? Okay, so of course there is a okay, let me state two open problems here. before. I will comment on this result, but let me first state two open problems. So open get rid of the log factors. I think it would be interesting to have the whole picture in which you don't need to add these extra log factors. Open problem number 2. Of course, is repeat this or prove a similar theorem. So this is, I think, okay, for 2 hidden layers. So I think this is difficult, perhaps, but this is, I think, an order of difficulty bigger than this one. All right, so this is similar. So there is a third problem is, of course, is tracing all the curve in the poly, when this ratio, when this ratio is of order 1, but that it's even more difficult.
But just a question, the 2 hidden layers you still mean in the MTK regime?
Right. So just take the 2 hidden layer in the NTK regime, so the linearization of the NTK. Now the kernel, the infinite width kernel, I already explained that is just the same inner product kernel. I mean, it's not the same, but it's an inner product kernel for which we have a precise characterization already. But okay, so we would like to prove this equality there. Okay, and you would expect now there's gonna be two n here, two width, and so the right ratio should be something like n over the number of sample size over the number of parameters. But of course, such a naive thing will not work, because if the first hidden layer is much smaller, then you will lose expressive power, right? So if the network is 1, so the input is this, and then there is one layer like this, and 1, and then there is another layer here, and 2, and then there is an output. Now in this case, the number of parameters is n1 times d, roughly, plus n1 times n2. Okay. But I don't think that the extension of this theorem to the 2 layers is that the error is small n over n1 d plus n1 and 2. So this is, so a naive extension would be n over p, which is basically the same order as n divided the max of these 2. I think that the right extension is probably n divided the mean of the 2. Okay. So I think this problem number 2 is difficult, and actually I'll comment later even on this. The reason it's difficult is that the kernel is no more a sum of independent terms. Okay, so in pictures, what this theorem tells me is, so if you do simulations for neural tangent regression, you see something like this. As n increases, or nd over n increases, see 1, and so you take a target function f star that is not a low degree polynomial, and you fix n to be bigger than dl, much smaller than dl plus 1. You can compute the risk of kernel ridge regression. You can run kernel ridge regression for this f star and get this risk. And then if you do a simulation for finite width kernel, what you'll see is something like this, that for the ridgeless case, so for lambda equals 0 plus, you see the divergence here, and then this goes down like this. Okay, so it goes asymptotically to the risk of kernel ridge regression. So this theorem, what it's telling you is that if you are down here, if you are above log nd to the c, this theorem says that these two match, right? And so removing the log tells you that indeed the two start matching when this is a big constant. Of course, it would be nice to get the whole curve. And of course, if you add lambda positive, you see something like this. Okay? So lambda positive, again, asymptotically here has no effect, but it has an effect there. Right? Another way to illustrate this is so in particular, this implies, so in particular we get benign. Since in this regime we saw that for kernel ridge regression lambda 0 is optimal, so we have also in this case benign overfitting. Okay, another way to illustrate this is to look at the plane, so to trace a phase diagram in the plane that is log number of parameters over log, let's say log dimension, and here log sample size over log dimension. Okay, so again, if you look at ridgeless regression, and you find figures in the paper, okay, there is a line that is the line at which the number of parameters become bigger than the number of points, and this is where we would expect, and in fact empirically where it starts happening, that you can interpolate the data. So on this side you can interpolate, so you can reach 0 error. On this side you cannot interpolate. So this side the train error is 0. On this side is strictly positive. We don't prove this. If you look at the risk is very large here. Okay, and then it decreases on the two sides. So this is this divergence that I'm seeing here. Okay. And then it decreases on the two sides, right? So on this side, it decreases and it converges to a limit. On this side, it decreases and converges to a limit, and the limit depends on. If you move along this line, you converge to a limit, and the limit depends on the ratio here. Okay, so here the limit will be. Okay, let's do it a different color. Here the limit will be large, and here will become smaller, and here will become smaller, and so on. Okay, because here you get polynomial ridge regression with degree 1, degree 2, etc. Okay, so this is the picture. You converge to a limit. Of course, one is curious of knowing what happens on the other side. We don't prove it in this theorem, but actually we know, we have an expectation of what happens, and we can do it. We can prove it in the random feature case. What happens is something very curious. It's completely symmetric. Again, this part of the picture was proved only for the random feature model. So regression, so this part is so above diagonal. Proved for kernel random feature, that is 1 over n, sum over I, 1 to n, sigma wi transpose x1, sigma wi transpose x2. And what happens is that it's completely symmetric. I mean, it's completely within the accuracy of the theorem. Here you converge to the same limit. Here you converge to same limit, and so on. And here you converge to the same limit. So here what happens is that here the sample size increases, but you are somehow limited by your approximation power. Even if even if you have a lot of sample size, you cannot fit the high degree part of your function because you have only capital N D parameters. So there is this divergence here. The divergence disappears if you put a regularization, and here, on one side you are, data limited, or statistical error dominates, and the other is approximation error. Limited or approximation limited. So this tells you that in practice, right, if you think of this as your plane of possibility, again, if you are committing to nature or your company gives you a certain amount of data, and what you should do is operate in the regime in which you are data limited, right? You should use all of your parameters. Okay. Okay. So I can add the third open question is prove the picture above open 3. Is what happens above the diagonal. For NT. For RF was proved, again, that is a paper with Theo Misekiewicz and Songmei. Below the diagonal for NTs, this paper with Ichao. Any questions? Yeah.
High-level question. I mean, I understand that these problems are kind of mathematically curious, but bottom line is that if we want to do these things, we just run polynomial kernel regression.
Right.
So
But
we are not winning anything by doing it with two-layer network with a certain width.
Right. I mean, okay. So this is in this. You are not winning anything by doing a kernel method. A neural network will work better. Actually, I will give separation example. If you go out of the linear regime, do we win anything by doing kernel regression with respect to this kernel with respect to polynomial regression? Well, the point is that polynomial regression really is something that you know because you know how to diagonalize the kernel. You know the distribution of the data, you know the eigenfunctions of the kernel, and you took, now in reality, you don't know the distribution of the data. You come up with a kernel, and then, you don't know what is the diagonalization. But yeah, in general, if you could tell me, I know the distribution of the data, you can take any kernel, diagonalize it, find its whole eigenfunction, and run a regression with respect to the top so many eigenfunctions. And this should be roughly equal to kernel regression. Okay. So of course here there is another interesting problem that is, does that make sense?
It does make sense. So you're saying, and here you assume the particular distribution of the data.
Right, because here.
You expect that this kind of
I mean, so you can prove weaker results than these ones, in which you know, if you have a kernel, then you can take, approximate it by, this is a sum, is always a sum of eigenfunctions. So any kernel, not necessarily an inner product kernel, say that I take, a 20 layers neural network with convolutional layers, etc. I can construct the kernel, okay, will be functions. Actually, there are programs that people at Google have developed for constructing this kernel. And then you can, in principle, look at it as an operator is in the space with respect to distribution of the data, and then diagonalize it, right? That's always possible. In theory, it's possible. Okay, there exists always such a decomposition. And then you say, okay, I'll take this to be some, I'll approximate this by some finite approximation, right? And then I'll take, probably if you take, so truncating to capital L means reducing the infinite dimensional regression to a regression with respect capital L parameters. And the general philosophy should be that if the number of parameters is much bigger than the sample size, this truncation is good, right? Because so should be that if L is much bigger than N, this truncation is okay. So here we're proving a form of this statement, right? But this is a perfectly, meaningful statement and makes perfect intuitive sense, right? And probably with some, some loose factors, it's possible to prove it in general, right? So now the problem with this is that this A, you don't know how to do this diagonalization because you don't know the data distribution. Even if you knew, now you have a symmetric, a self-adjoint operator in RD. It's like, diagonalizing is like solving the eigenfunction of the Schrödinger equation in D dimension. So for D particle, D electron, so it's very, very difficult. Suppose even that you do that, it's not even interesting to do it, because once you do it, you are reduced to do regression with respect to capital L parameters, and this will have complexity that is n times capital L at least, right? So you will not simplify the computationally the original problem. So here there is a open problem number 3.
4.
What? Well, 4. Yeah. So here one interesting fact of this thing, if you think in terms of random features, any kernel, you can view it. So if you give me any kernel, I can always write it as so for any kernel kx1, x2 can be written as is equal to the expectation of W transpose. Okay, let's write expectation of x, W theta 1, x1 theta, x sigma x2 theta for some distribution of theta. Let's call this sigma bar and p theta. So any kernel can be written as the random feature kernel for a certain activation function, etc. And so this suggests another numerical approach, that is, I approximate this by this. And then I run a finite dimensional regression here, right? The problem with kernel methods is that they are very expensive. I mean, they scale polynomially, not linearly. So you can approximate. So this was the idea of Rahimi rect. They didn't start with the random features. They start with kernels. Say, okay, let's see how can we solve kernel numerically. Yeah? And so this gave rise to a whole line of work that is about, randomized methods for solving, kernel regression. So the open problem, okay, I stated a bit, vaguely. Open number 4 Okay. As we'll see, there is separations between kernel and neural network, but in some cases, kernel work pretty well. And so there is a whole research program that is how fast can we solve our empirical risk minimization in kernel spaces. Okay, so this, okay, even in the case of kernel ridge regression is an interesting.
I didn't understand. I don't know. I must have missed something. I didn't understand. I understood the point of
Right.
designing the Kiojan function, then you take a finite width limit. I don't
Right.
understand how it's related to this question.
Well, because this gives one method. So you want to solve this, the standard, the classical way that you find in textbooks gives you a regression with, lowercase n parameters, okay? So the number of parameters in your regression scales like your sample size, and so you have now complexity depending on how you solve it, but at least n square, right? On top of that, also at prediction time is what is very inconvenient of kernel is that at prediction time the complexity is n square. Okay, so these people said, okay, let's take this approach. Now the complexity become capital N times lowercase n. So perhaps if I can take capital N small, then I'm fine. By the way, this plot says that I cannot, if I want to be optimal, I should take capital N of the order of lowercase n. Okay, optimal. So in this setting, there is no gain in doing this Rahimi-Recht trick, right? But okay, you can ask now the question more generally. Can you come up with other ideas for solving kernel ridge regression, for instance?
Faster in terms of implementation.
Right, faster than in terms of. By the way, at prediction time, what is interesting is that while this is at prediction time, while this is n times d, the random feature model. Okay, so remark. So given all these results, it seems that the random feature model is similar to the neural tangent model, but here is a point in which the neural tangent model wins. So at prediction time, the random feature model has complexity, what has complexity? N times d. That is equal to the number of parameters times d. Okay, and the number of parameters is what controls the generalization error. While the NT model at prediction time has complexity n times d, because again, the matrix vector multiplication is what dominates, but the interesting thing is that this is p times d. P times d is p. Okay, so in terms, if you fix a certain generalization error, you fix basically the p. And the p is what drives in both models the generalization error. But here, if you fix the p at prediction time, things becomes much more complex. Where here, you don't get the extra factor p. Right, so this is one way in which neural tangents are better. Okay. So in the rest of the lecture, what I want to do is that I want to describe a little bit of techniques, and in fact, I will not prove this theorem, but actually I will look at so one piece in the proof of this theorem is proving characterization of the kernel matrix, and so I state and describe the proof of that theorem. So the structure, so the kernel matrix Okay, so we have two kernel matrices, Kn and then, so this is the infinite width. So these are two n by n matrices. So this is the finite width n by n kernel matrix, and this is the infinite width. And the theorem is okay. So this theorem is for deterministic x. So I will not assume anything about the data points. So assume x1, xn deterministic such that two things work. The minimum singular value of Kn is bigger or equal than V of sigma divided by 2, which I defined before, and the operator norm of x, okay, what is x is the matrix with the row xi's, is less than 2 square root of n plus square root of d. Okay, so give me any n data points that satisfies this condition. You can compute the n by n kernel matrix, and this minimum singular value is like this. And you can compute the n by d matrix of data points, and this maximum eigenvalue is like this. Maximum singular value is bounded like this. Why I choose these two constants here, this and this? Because, okay, we know by random matrix theory, this is basically, if I take the x's, uniform on the sphere, or if I take Gaussian or many other distribution, this is the typical value is this one. So I put an extra factor 2 because I don't care about constants. And we saw in the last lecture that the minimum singular value of the kernel is this one, and I put an extra factor 2 to give me some leeway. Okay? So these conditions are verified with high probability for random x's. With the distribution that I gave before, but this specific theorem doesn't assume the x's to be random. Then, with high probability with respect to W1, Wn, so these are always uniform on the sphere, as in the previous lecture. Then what you obtain is Kn minus 1/2 Knn Kn minus 1/2 minus identity. Operator norm, this is less than what it should be, n log nd divided nd. Again, here the log, this log is spurious, as do, and perhaps there is a constant here. Okay, so let's look. Here I'm looking at basically a distance between the finite width kernel and the infinite width kernel. Now, in operator norm, now the most natural way of measuring distance would have been, so it's very important in proving this theorem, figuring out that the right way to measure the distance is this one, because if you do it in other ways, it's very difficult to prove this theorem. But in this way, as you'll see, it's quite easy to prove this theorem. And the reason why that is the right way, so the naive distance so the naive idea naively, you would have said, okay, I have a random matrix that is a sum of IID matrix. I have its expectation, and I bound the maximum eigenvalue of the difference, right? But what happens is that this matrix has very large eigenvalues. Remember that the eigenvalues of Kn of the expectation, as we saw in the last lecture. So the largest one is of order n, and then there is a bunch of them of order n over d, and then there is another bunch of them of order n over d squared, and blah, 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 until you arrive at order 1. So this is a matrix that, it's different from typical expectation, typical empirical covariance matrices that you look at that have bounded condition numbers. This has very large separation, and so when you add some noise to this, you would expect that the noise has a large effect here and a small effect there. So it's nice, it's much better to rescale this by Kn as we are doing there. Okay? And let me notice, by the way, that as a corollary, of this theorem, so under same assumption, if nd is bigger than n log nt, or n log n to a c times constant c, for any y1, yn, there exists a b such that f xi b equal yi for each I. Okay? So there exists an interpolator. Okay? A simpler question than the questions that we are looking at here is how many parameters do I need so that there exists a model in my class that can interpolate perfectly the data. Right? In this setting, this reduces to a system of linear equations. And when does a system of linear equation have a solution? Well, you need this matrix to be full row rank. Okay? And if the minimum, this is telling you this matrix is really phi times phi transpose, right? So this tells you that the minimum eigenvalue of phi transpose is bounded away from 0, and so the row rank, this is full row rank. Okay, so this is a consequence of this. So here there is another open problem. Is as far as I know, this is the best rigorous bound on the interpolation threshold. Of course, we expect that nd equal n is probably sufficient. So prove that. So you expect 1 plus epsilon times n sufficient. Okay. Very nice. So now, what is the proof of this theorem? Is very easy, and it uses, what I said last time is a very useful random matrix theory fact, that is matrix Bernstein inequality. Let's see. So these are what I called in the last lecture the most useful fact in random matrix theory. So if all of this was boring to you, it's a moment to wake up and listen to one interesting theorem. We say the following. So let's say that I have xi symmetric, so I less or equal than n, symmetric IID matrices. And I'll define two quantities. So what is Bernstein inequality? Is something that bounds the tail of the sum of the xi's in terms of the variance of the xi's and the maximum of any of the xi's. Now I have to define to you what is the variance and the maximum in this setting. So in this setting, the variance, or the proxy for the variance, is defined as the operator norm of the sum of the expectation of the squares of these matrices. And the maximum is defined as the essential sup of the maximum of the norm. Okay, what does this mean? Is the essential sup means that this is a random variable z. The essential sup is the smallest deterministic number such that z is less than m almost surely. Okay? So in other words, I want that p of the max over L of this operator norm less than m is equal to 1. This is equivalent. Then the following happens. You center these random matrices, you look at the operator norm, you want to know whether this is bigger than t, this is less than 2d exponential of minus t squared over 2 sigma squared plus 2 thirds mt. Okay, so morally, okay, so this gives you a tail bound, goes down in t, and you see it's really the minimum of t squared over sigma squared and t over m. So morally, this says that, morally, not morally, but mathematically, this says that the operator norm of this is less or equal than, okay, the maximum of two numbers. One is the variance term, so is sigma square root of log d. And the other maximum with m log d. Okay? And here the fact that I put the twiddle means that I'm neglecting a constant factor in front. Okay? So if you are even coarser and forget log terms, so the value is less than the variance and the maximum of any entries. Okay? So this is exactly what you would do for random variable, except for random variable you don't have these log d factors. Okay? In fact, the classical Bernstein inequality, you recover it if you assume that these are one-by-one matrices. Okay, now if I look at my object, Kn entry ij is what? Is 1 over nd sum over L 1 to n, and then xi xj sigma prime of wl transpose xi sigma prime wl transpose xj. Okay? So let's write it in a nicer form. Kn is 1 over nd sum over L 1 to n. And then you see this is, you can think of this as a diagonal matrix acting on the left of this, and this is a matrix, and this is a diagonal matrix acting on the right. So I can write this as dl times xx transpose times dl, where dl is the matrix with entries diagonal of sigma prime wl transpose xi. Okay? So this is the matrix whose rows are the xi's. So you have xx transpose, dl on the left and dl on the right. Okay, and so, okay, let's see. So now if I look at k minus 1/2, now I'm dropping all the subscript lowercase n. This is what? This is, okay, 1 over n, sum over L, 1 to capital N, and then there is HL, where HL is k to the minus 1/2 dl x transpose dl k to the minus 1/2. So these HL are IID matrices because, you know, if you fix the axis, the W's are IID. So these are IID matrices. So I'm exactly in the setting of matrix Bernstein inequality. So what I want to do, I want to bound the variance and the maximum entry. Of course, E of HL is equal to the identity because, okay, it's equal to k minus 1/2 times the expectation of this, which is exactly k times k minus 1/2, and this is equal to the identity n by n. Okay, so everything reduces to a matrix concentration inequality. Yeah, so this is good point, good reminder. You know, as you see as you will see, the proof of this theorem is very simple for 2 layers, one hidden layer neural network or 2-layer neural network, because these matrices are independent. Okay, and even this is a piece of the whole theorem because bounding the risk requires also to control the eigenvectors essentially. It's the easier step of the whole theorem, but even this, in the case of 2 hidden layers, you know, the best result that I know, perhaps there have been better, but a few months ago there was a result by Ige Zhu, but it requires, I don't remember exactly the width, but it requires a width that is much larger than what you expect. You know, it's still polynomial in D and the sample size, but it's something like with the wrong exponent. I don't know if it is n squared, but you know, it's a wrong exponent. I think it requires this.
And I know very little about this Bernstein things, but isn't this recent work by Afonso kind of going in the...
No, this okay, so this is, okay, there have been all sorts of refinement, including Afonso, etc. But this, okay, so the first form of matrix concentration inequality that is not this is matrix Chernoff, is Alswede and Winter. Rudi Alswede. Interestingly, they proved this in a paper in information theory transactions on quantum information theory. Okay, because you understand why? Because in you know, these are measurement matrices in a quantum information theory problem, and then was really introduced to the statistics, high-dimensional statistics world. Yeah, now I'm blanking on the name. No, there was a paper on matrix concentration in any basis, in matrix recovery in any basis that is, no, I'm ashamed, I forgot the name, so I remember it, paper on matrix concentration. And then that used Alswede Winter, and then Joel Trop really proved that this form of the theorem in which you have which is more useful than the original ones, but because it has this variance. You know, the Alswede Winter basically bounded everything in terms of capital M. while this other paper, this paper of Trop. And there is a very nice review paper of Trop that is a user-friendly introduction to random matrix theory or something like that. And therefore, there have been, you see here there is a problem that is these log D factors. This gives you always, often a log D factor that shouldn't be there. For instance, if you apply it to bound the norm of Wigner matrices, you get square root of D log D instead of square root of D. And this comes because of this. And okay, so this has been improved. There are, matrix concentration inequality that work in infinite dimension. Karim Lunici and
So you are saying for non-IID or weakly independent somehow there is not much?
weakly independent what? Matrices?
Yes, matrices.
Well, that is another line of extension. You can extend this to martingales. So this is actually how we prove, in the last lecture on the kernel method, I had two approximations, one for high degree and the other is for the low degree part. And the high degree part is using matrix concentration for martingale, and that was proved by Roberto Oliveira. And then there was, the first form by Roberto, and then there was a stronger form again by Joel Trop. Yeah. David Gross. Fantastic, thank you. Yeah, I'm really ashamed. I don't remember this. Sorry, it was also, also it came to this, he knew of Alswede-Winter, of course, because, so you see, this is a nice fact about science. You want work on quantum information theory, and then because of that, you read a paper by Alswede-Winter, and then you find out a way to apply it to high-dimensional statistics. So it was an interesting story. Okay, so now, since it's a sum of independent random variables, we have that by the matrix Bernstein, this is less than, there is an extra factor 1 over n, because this is, I put the 1 over n out explicitly, and then there is m log d, maximum of m log n. In this case, the size of this matrices is n by n, and sigma square root of log n. So now I have to compute m and sigma. So for m, I must bound the worst case operator norm. So now I realize that I forgot one piece here. Here there is this 1 over d, so I'll put the 1 over d here. So I put it in the definition of HL. Okay, so this you get what is 1 over d, and then 1 over lambda mean of k. Okay, because you have this k to minus 1/2, k minus 1/2, and then you get the operator norm of dl, and then the operator norm of x squared. And now let me make an assumption. We don't use this assumption in the paper. Let's assume that sigma prime is finite. Right? For instance, ReLU of tangent, the first derivative is bounded, right? So this implies that this is constant. And so by assumption, this is lower bounded by constant. So this is less than 1 over d. This is a constant. This is a constant. And this is square root of n plus square root of d. And then there is a square. And let's assume, to simplify formula, let me also assume n bigger than a constant times d, which simplifies a little bit the calculation. In any case, it's the interesting case, because if you have less points than dimension, you are in trouble. So this is less than n times d. So this will be my m. Okay, now what about sigma square? Is this calculation okay? Let me compute sigma square. Sigma square is 1 over D, and then is the operator norm of sum over I L 1 to n, the expectation of HL square operator norm. So all of these expectations are equal, so this is equal to capital N times the expectation norm of the operator norm of the expectation of, let's say, any of them, H1. And okay, what is the expectation of H1 square? Okay, there is a factor 1 over D, if you remember, and then there is the expectation of K minus 1/2 D1 X transpose D1, and then the same, right? K minus 1 D1 X transpose D1 K minus 1/2. Did I forget anything? And here the expectation is with respect to the W that is hidden in D1. So the expectation is with respect to W1. Right? So remember that D1 is diag of sigma prime of W1 transpose Xi. So again, under what I was saying before, under the sigma prime bounded, if sigma prime is bounded and K, the minimum singular value is K is bounded away from 0, this whole matrix here is operator norm bounded by constant. Because D is bounded and K minus 1 is bounded, right? And now, okay, this is the typical thing that one makes always mistake, but you should check yourself. You know, there is so many mistakes in papers about this kind of inequalities, but this is less than, if this is bounded by a constant, okay, this is less than the operator norm of A transpose times the operator norm of M. Check it yourself. So if you do this, then I get less or equal than.
Sorry, it's back to 1 over D squared.
1 over D squared, thank you. Thank you. So now I can pull out that, and so I get the expectation over W, and then the K minus 1/2 is deterministic, and then expectation over W of D1 X transpose X transpose D1 K minus 1/2. Is that okay? Okay, again, let me repeat the same trick. This guy is bounded by, square root of n plus square root of d square, so less than n, if I assume this regime in operator norm. So this is less than, I'm forgetting the d square, n over d square, K minus 1/2 E of W D1 X transpose D1 K minus 1/2. Okay, so far what I did was very brutal. I just bounded everything by supremum operator norm, but now the power so the power of this inequality is really that I'm taking expectation here. So I'm not taking the norm inside, I'm taking the norm outside the expectation. Now I can take this expectation here. Now this matrix, worst case, can be quite large, can be n, but so the expectation is actually K, right? So 1 over D times this is exactly HL. So let me rewrite it as n, or over d square over d, k minus 1 half expectation of HL or H1. And so this is the identity. Okay, so let me check now that I didn't. Yeah. Okay, now we are in great shape. We can put everything in there. And okay. Did I do some mistake? So very simple calculation. We obtained that what we wanted to bound, k minus 1 half kn, k minus 1 half minus in, operator norm is less or equal, and then we have the first piece is n over nd times log n maximum with and then sigma, you get so there is a square root of n here. So this, if I put it in here, this gives me n times n over d, right? And then I take the square root and divide by n, so you get square root of n and d. Okay, so in the regime that we are interested in, the overparameterized regime, this is the worst case. So this proves the theorem. Yeah, of course.
So when you write down this inequality with the operator norm, you actually have an expectation inside of the operator norm, right? Because you have the operator norm of the expectation.
Which?
So you're trying to apply that inequality, but you have an expectation. So let's say the operator norm of the expectation A transpose.
You're right. This is the inequality that I'm using.
Yeah.
Right? That this is dominated by that, right? So this concretely what it means is really that for any vector v, A M A transpose v is less or equal than V A transpose v. Okay, which is clear because I can. Okay. If M is less than constant times the identity deterministically, then this happens, right? Just because you call A transpose times V, you call it V prime, right? And now this means that if these matrices are random and M satisfies this almost surely, then I can take expectations on the both sides.
Thank you.
Can you repeat why you expect the property to hold an average for the k
Sorry?
minus 1? Can you repeat why you expect the property m less than identity to hold for k to the minus 1?
Because we assume in the statement of the theorem, remember that one of the assumptions that I made was this one, that lambda mean of k is bigger or equal than V sigma over 2. So and we proved in the last lecture that if you take random data, this holds with high probability, right? So the theorem, as I stated, is I fix the axis So there is, if you want, there is a set calligraphic K of possible realization of X's such that if, first of all, this holds with high probability, is close to 1. So your data belong to this set with high probability. And second, if your data belong to this set, then you have these bounds on the operator norm. Okay? So I'm taking the X. Yeah. Okay, by the way, you know, in the last lecture I stated that I didn't prove, you know, a fact about the kernel matrices. I had this thing, right? This condition that the matrix that I called Ym, the matrix of empirical matrix of spherical harmonics, is approximately orthogonal. At a certain point, I said this was somehow the smooth part of my kernel. This you prove basically by the same, by same application of the same theorem. So it's a nice exercise. And the other part was that for the high frequency, this is this matrix 1 over, instead, for the high frequencies, what happens is that Ym transpose is close to a constant times the identity. So this was the low frequency, this was the high frequency, high degree. And this instead you prove by doing the martingale difference of this matrix concentration, martingale version of this matrix concentration inequality. So, yeah, more exercises. Is there any? Okay, I'm over time already, but yeah. If there is any question. Yeah.
Very basic question. Why did this become an expectation?
Ah, good point. Didn't become an expectation. So this is with high probability bound. Yeah. Other questions? Okay. If not, let's go get coffee, I guess.